Okay, folks, we can get going. Any questions before I get into content stuff? Any pending Lab 2 questions? Any Lab 3 Week 1 questions that I can help address? We've had a couple of students build the motor control board, and seems to work. So that's very exciting. Always makes me feel better. The one gentle, well, not really a modification, but when you get that motor control board built, call a member of the lab staff over so that we can help you get it set up from a, get it hooked up to the power supply. We're going to be supplying the 12-volt power supply to the FET from the bench power supply. Experimentation shows that the motors work nicely if we power them, the 5-volt power supply, from a wallward. They can push a little bit more current, so you get a little bit more oomph out of the motor. But we'll help you set that up. Any other questions about any of that stuff? I wanted to just remind you, too, that your last lab report was due on the Friday at the end of a week, and that was because we had a break at the beginning of the week. So I just wanted to remind you that we're back to the regular schedule now, where your lab reports are due at the beginning of your next lab section. So for instance, if you did your final checkoff for Lab 3 yesterday afternoon, for Lab 2 yesterday afternoon, your Lab 2 report would be due at the beginning of your lab section next week, right? That makes sense? So just pointing you again to this schedule of due dates that lives on the course page in case there's any confusion. Okay, anything from anyone before I get going? Like I said last time, my plan for today, given that your final project proposals are due in a little bit over a week, I thought it might be productive for us to just brain dump ideas. So my plan is to just, I have a list here of, hallucinations that I'm going to talk through. But to the extent that anyone would like to volunteer their own ideas, that would be perfectly welcome. Yes? It's a good question. So the question was, for final projects, do you work with your lab partners? Usually, yes. Though if folks want to change lab groups for the final project, that's okay as well. I do strongly advise that it remains a group project, however. So just like for the lab assignments, I recommended groups of 3, groups of 2 being okay. Likewise for the final project. Any other questions about the logistics of the final projects? Bruce? Demo date, slightly to be determined. I will let you know. What do I have listed here at the moment? I have final project demos the week of 5/5. I think that's the last week of class. That gives us, if I scheduled this, if I remember correctly, that gives us about 5 weeks of final project time. I think including spring break, though. 1, 2, 3, 4. Yeah, so 4 or 5-ish week of final project time. That's a lot of time, which means you can be ambitious here with these final projects. Part of the reason that we ask for you to put a proposal in is we want to, mostly what we're doing with these final project proposals is helping you calibrate for scope. 4 weeks is a long time, right? So you can do a pretty complicated project in that time. We want to make sure that what you've proposed is sufficiently complicated. It is also very easy to propose a project that is scoped better for, say, a PhD. And so we're going to try to help you get it right. But that's why we ask for this about a week before you start the final projects, so that we have some time to iterate on your ideas if need be, to get them scoped about right for the amount of time that we have available. Okay. Any other questions about final project stuff? Okay, that being the case, I'll get going with just brain dumping stuff. And like I said, interrupt me at any time. The ideas I have listed down here are in no particular order, and they sort of fall into a few broad overlapping categories. The first broad category that just happens to be on my list is projects that are related to, you might say, mathematics, physics, and natural modeling. This is sort of a fun whole class of projects. For example, has anyone ever heard of diffusion limited aggregation? Let's see here. If you have gotten out of bed on a frosty morning in Ithaca and looked at your windows, you may have noticed that on some particularly cold mornings, there's really interesting ice crystal patterns across the window. You see this on vehicles a lot as well, on cold mornings. The process by which those crystals form is well modeled by diffusion limited aggregation, which is very much like a particle system. So the idea here is that we have a whole bunch of particles sort of randomly moving about the screen, and you have a seed particle or a series of seed locations that are fixed. And in the event that one of your wiggling particles wiggles up against a seed location, it sticks and stays. So it's a very simple algorithm to implement. It is very, very parallelizable. And if you run this, you end up with these really gorgeous crystal structures forming on the VGA screen. This is particularly fun on the RP2040 because you can generate, as evidenced by your Galton board lab, a ton of particles, right? And the rules that describe the behavior of each particles for the diffusion limited aggregation project is actually simpler, I would say, than those that describe the behavior of the particles for the Galton board. Just to say, I'll bet you could get even more for an animation rate timing deadline. These make for really, really beautiful demonstrations. I've had some students do this in the past. These are just a blast. Sort of similar, I mentioned that these are kind of like particle systems. Let me just clarify what I mean by a particle system. Particle system simulation. A particle system simulation is one in which you model whatever it is that you're trying to simulate by as many particles as you can manage at the animation rate that you want to achieve. And you describe a series of rules that describe how those particles move as a function of their position on the screen, for instance. So you could imagine one way of thinking about a lot of these particle systems is the particles are little particles, and they exist in a vector field of your design that's sort of invisible here, that describes if the particle's here, it gets bumped this way, if it's there, it gets bumped this way. And depending how you design that vector field and where you place those particles and how you colorize them, you can get really beautiful simulations of things like fire or explosions or smoke or water. And on the RP2040, you have enough compute and enough memory to do enough particles to make these really compelling. I've had some students in the past make really nice particle simulations of waterfalls. So they modeled water as a bunch of particles flowing off of a cliff. So the motion of all of those particles had gravity associated with it. And then when it encountered a rock, it would sort of splash. And there was a series of rules that described what happens to each particle when it hits a surface. And it makes this really nice simulation of what looks a whole lot like a waterfall. They managed to get a waterfall simulation that included, if I recall correctly, like 12,000 particles. Enough that it really looked nice. If you're a fan of Star Wars, the in-space explosions in all of the original Star Wars movies were, to my understanding, all particle simulations. It'd be kind of neat to try to do an RP2040 version of an in-space Star Wars-esque explosion. So that could be another kind of fun project. Slightly different, but also sort of related to nature modeling. Let's see. Diffusion, oh, sorry. Talking and typing. Diffusion reaction model. Let's try that. These diffusion reaction systems, these aren't particle systems per se. What they are instead is a series of coupled differential equations that you integrate over time. And those differential equations have some knobs that you can turn to sort of describe how they evolve. And what they approximately model is a system in which you have some substrate chemical. So you can imagine you painted the VGA screen with some chemical, and then you splotch some other chemical on top of that substrate chemical. And what the series of coupled differential equations models is the process by which those splotches of chemical diffuse, and as they diffuse, they also react with the substrate chemical to produce a third inert chemical that doesn't react. And what's fascinating about these is depending on how you turn the knobs of this system of coupled differential equations, the patterns that you get out are, first of all, just kind of interesting and beautiful. And second of all, you turn the knobs just a little bit, and all of a sudden, there's like giraffe spots. And then you turn it a little bit more, and all of a sudden, there's something that's very recognizably like leopard spots or tiger stripes or something like that. So this is a really good model for how animal coats actually form. And if you build yourself a system that allows for you to play with these parameters, you can sort of discover animal coat patterns kind of naturally. And you can also create animal coat patterns that don't exist in nature, but that could exist because they would abide by the same sort of underlying principles. By the way, fascinatingly, there's a famous paper that describes these whole systems written by Alan Turing, of all people. One of his many contributions to like 15 different fields or whatever. This was one of his big contributions to, I don't know, whatever field you would classify this in, right? And the name of that paper, it has some really kind of cheeky title, something like How the Tiger Got His Stripes or something like that. So these are really, really cool systems. Again, if you're into, I really like sort of aesthetic mathematics systems. And I like projects that have the property, the thing you built has the ability to surprise you, the person that built it. That to me is just a very interesting property of an engineered system. This would have that property. If you built this, or if you built those particle systems, by the way, it has that property where the thing you built, though you built it, it will do things that surprise you. And it'll make delightful patterns that you wouldn't have expected, perhaps. I just think that's a really neat property of projects. Also sort of mathematical, and perhaps a little bit more familiar, there is, of course, the Mandelbrot set and its cousins, the Julius sets. The Mandelbrot set, as is probably familiar to many of you, at least you've probably seen this picture before, even if you haven't discussed it in a class. The Mandelbrot set is probably the most famous fractal. It has been called the most beautiful structure in mathematics, which is a title that, in my opinion, I think it probably earns. It's pretty darn stunning. This whole very complicated structure is generated by an extremely simple set of rules. What you do, in brief, is you associate each pixel on the screen to a coordinate on the complex plane, right? So you can imagine our real axis is here, our imaginary axis is here. So for every pixel location, there's a corresponding complex coordinate. You run a really simple iteration over that complex number to see whether it blows up to infinity or whether it appears to be staying stable, not blowing up to infinity. If it does not blow up to infinity, we say it's in the set. If it blows up to infinity, it's outside the set. So it's incredibly simple to implement. You run that over every pixel on the VGA screen, and what appears is the most beautiful structure in mathematics. It's surprising and really delightful, and you could imagine, you know, this has a whole bunch of interesting properties. Perhaps one of its most interesting properties is the edge of this looked kind of rough, which kind of raises a question, which is, well, how rough is it? The answer, as it turns out, is infinitely rough. What that means mathematically is you can zoom into the edge of this Mandelbrot set, and what you will find is more twisty, turny, curvy edges that are sort of aesthetically similar, but not identical to any of the edges that you would have seen before. You can zoom in forever on an edge, and you never find a point at which it's just like straight forever. It continues to twist and curve and bend the whole way down. So you can imagine building an interface that allows for the user to render this and then perhaps explore it a little bit, zoom into the edges and so forth. There is also, I'll just mention some very interesting connections between the Mandelbrot set and Cornell. Some of the properties of the Mandelbrot set, including its connectedness. You look at this, and at this zoom level, you might see some little, what looks like islands out here of stuff that's in the set that appear as if they may be separated from the rest of the set. Some folks here at Cornell were able to determine that no, in fact, if you could zoom in far enough, you would see a little tendril coming out here, making this set fully connected. It was Hubbard and Dowdy were the folks, with the help of Homer Smith, one of Hubbard's graduate students, with the help of the Theory Center at Cornell here, Cornell's supercomputer, being run at the time by Bruce, who helped to generate some of the images to figure out the Mandelbrot set here. I mentioned that the Mandelbrot set has some cousins, in the Julia sets. If you tweak the rules by which you do those iterations just a little bit, you get a whole different family of beautiful fractals coming out of this. So this is interesting mathematically. The other interesting thing about it is, though it is simple mathematically to generate, it takes a lot of compute. You have to do a bunch of multiplies. And so it makes for a very nice visual demonstration of optimization techniques. And so I could imagine a really cool project that uses the Mandelbrot set as your demonstration of how much your optimizations have gotten you in terms of compute time increases, or decreases, I suppose. So for instance, I could imagine you crack open the RP2040 just straight out of the box, implement a naive version of the Mandelbrot set, and time how long it takes to draw the whole thing to the VGA screen. With no optimizations using floating points, it's probably going to take a couple minutes to draw this whole thing. And then you start overclocking and optimizing and so forth, and you see how fast you can get this to be drawn. This, by the way, if you're interested in this, you might consider taking 5760, the FPGAs class that's similar in structure to this one but uses FPGAs. One of the labs in that class is to build a specialized computer that just computes this. Fastest I've seen a student render this thing in 5760 is 35 milliseconds. Pretty darn fast. Let me just show you the Julia sets, by the way, because they're pretty. Julia sets. This, like I suggested, it's not a single fractal, but instead a whole family. So here, too, I could imagine some interesting interface that allows for the user to generate these sort of in real time. Bruce? That was a great project. So the students in that case, they took the Mandelbrot set, they chunked it up, and then they built a networked connection of RP2040s, and each RP2040 was only responsible for a subset of the pixels associated with the Mandelbrot set. They would all communicate over a bus back to a single RP2040 that was drawing to the screen, so that they could be working on 16 different pixels simultaneously, 8 RP2040s, each RP2040 with 2 cores, right? So they could be, and they were measuring, you know, as we add more RP2040s, what's the time increase that we get? And they started to discover that, if I recall correctly, I think they added enough RP2040s, it became the case that the rate limiter was their bus, the speed with which each could communicate back to that which was serving to the VGA screen. Okay. Another fun one, are people familiar with cellular automata? The most famous example of this, Aiden's super familiar with cellular, Game of Life, which, by the way, I think is one of these Google things that, oh, you can't see it with the resolution of the, oh, you can kind of see it here. If you Google Game of Life, it's one of those fun Google things where Game of Life starts propagating across your web browser. Let me go to the Wikipedia page. So Game of Life is perhaps the most famous example of a cellular automata. A cellular automaton is a system generally composed of a grid of cells. In the most simple cellular automatons, each of those cells is in one of 2 states. It's either on or off, or dead or alive, or white or black, you know, whatever. It's in one of two states. And there's a series of rules that describe how from one generation to the next generation, a particular cell might transition from on to off, or from off to on, and there's a set of rules that describe, you know, if a cell is on, does it stay on? If it's off, does it stay off? And from a very simple set of rules, so for Conway's Game of Life, these are the rules that describe the transitions of each cell between generations. The verbiage that's used here is live and dead. This comes from the original articulation of this automaton by John Conway. This is how he was thinking about it. So any live cell with fewer than 2 live neighbors dies as if by underpopulation in the next generation. So that would transition a cell, you know, from on to off. Any live cell with 2 or 3 live neighbors lives to the next generation. Any live cell with more than 3 live neighbors dies as if by overpopulation, and any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction in the next generation. So he was kind of thinking about population dynamics as he was modeling these things. And it turns out with these 4 very simple rules, you can get unbelievable complexity. In fact, as it turns out, Conway's game of life, these 3 rules, is Turing complete. And God bless them, there have been folks that figured out how to build logic gates in Conway's game of life. And from those logic gates, they've built entire processors. And with those processors, they have built game of life in game of life. If you Google around on YouTube, you will find unbelievable animations of these things. So this is one example of a cellular automaton. There are others. Another fun example is Wireworld. Wireworld, world automaton. Another set of rules, okay, another cellular automaton. It's a different set of rules, so it leads to different behavior. This kind of sort of models electricity. And if you have questions about this, our own Aiden and lab partner in 5760 last semester built Wireworld on the FPGA and managed to implement a processor in it. God. And there's a whole bunch of other cellular automatons. If you Google around for these, if you're kind of into these things being, you know, essentially systems composed of lots of cells and a set of rules by which cells change state from one generation to another generation, and the emergent phenomena that occur as a consequence of those rules. Google around a little bit and you'll find a whole bunch of these. If you're really interested in this, the mathematician Stephen Wolfram did a pretty exhaustive study of one particular class of these cellular automata that you might be interested in reading about. Let's see. Other fun algorithms. The diamond square algorithm. If any of you have played video games with procedurally generated landscapes, what would be examples of this? I know Minecraft, I believe, is an example of this. Is Skyrim? Skyrim may or may not be, I'm not sure. In any case, even if it's not, those landscapes were likely generated algorithmically. The diamond square algorithm is one algorithm by which you can generate really nice looking landscapes. And I won't talk through the details of it, but essentially what you could imagine, you start with a flat plane, you displace the center, then you zoom into each corner and you displace those. And as you zoom in, you end up with really organic looking landscapes, sort of mountainscapes, where you can turn some knobs to adjust how high the mountains are and so forth. And so this allows for you to generate some really, really nice looking terrains. And then you could imagine imposing some very simple colorization rules like, okay, any place in this terrain that is below a certain elevation, I'm going to put a blue plane there. And that basically you're filling valleys with water in that case, like you're building these big ponds and lakes and so forth. And you might say, all right, anything between here and here, I'm going to colorize green. And then anything here and above, I'm going to colorize white. And you could get pretty nice looking mountains out of this, which is kind of startling to see. Also, similarly startling, L systems. Let's see here, L systems. L systems are different. L systems are not automatons. What they are instead is you start with a string of symbols, and each of those symbols represents some action to take. So for instance, you might have a symbol that means move forward a little bit. You might have another symbol that means turn right. You might have another symbol that means turn left. There might be symbols that mean turn right by this amount or that amount or so forth. And so you start with some base string of symbols, and then there's a series of rules by which symbols turn into more symbols, which turn into more symbols. And so you're starting with essentially a base case, and then algorithmically building upon that, where each symbol becomes more symbols. And depending on the particular symbol algebra that you choose and the rules associated with those symbol algebra, you can use them to draw just beautiful plants. and a certain set of rules will generate things that look startlingly like elm trees, for instance. Then you play with the rules a little bit and you get wheatgrass out. These two, if you're into like computer graphics, or if you're into exploring the relationship between nature and computing, stuff like this is just such a blast. Another example of algorithmically generated plant life that many of you have seen at this point, but I'll just point your attention to again. The Barnsley Fern is one of the VGA demos that some of you have run to just confirm that your code's working correctly. It too is an algorithmically generated plant structure. This uses a very different algorithm from L systems in order to generate this shape. Rather than sort of an algebra of symbols, this instead has a series of functions. You randomly select one point, you randomly choose a function that moves you to another point, you draw something there, choose a function moves you to another point, and this particular collection of functions, if you bounce around the screen a whole bunch, ends up creating a startlingly organic fern shape here. And here too, you tweak the numbers a little bit and the shape of the fern changes in really interesting ways. I could imagine a final project that uses this as some kind of a premise. Okay. More just fun fractal stuff. By the way, a lot of this, I brought this book. If you're into fractals and programming, there's a good book by Roger Stevens called Fractal Programming in C, just full of great stuff. I will bet that it's available in the library, but just to give you, some chapter titles here, we've got the Lorenz and Other Strange Attractors, Population Equation and Bifurcation Diagrams, Snowflake and Other von Koch Curves, Piano Curves, Hilbert Curves, Sierpinski Curves, Trees, Working with Circles, Mandelbrot Set, Dragon Curves, which I'm going to show you here in a moment, the Phoenix Curves, I don't even know what the hell that is, Brownian Motion, Fractal Landscapes. In any case, and it's all in C, right? So it's a great sort of just reference for if you're into this kind of stuff. It's a good book to go look up. What's the Dragon Curve? It too is another fractal. Has anybody ever read the Jurassic Park book by chance? Book associated with the movie? That book, every chapter of the book is another iteration. It starts with an image of another iteration of the Dragon Curve. So as you read the book, the Dragon Curve is building with each chapter. I think representing that book plays with the idea of chaos, right? And so it's playing with that idea. But this too, it's another sort of fractal iteration that ends up generating these, I think, rather interesting shapes. And so you might consider making yourself a Dragon Curve drawer. Here too, this is a whole rabbit hole. Hilbert curves, another fun one. Hilbert curve is really interesting. It's a fractal. It's a line-based fractal. This particular curve has the special property that it is a space-filling curve. And so if you iterate this over and over and over again to higher and higher resolution, your single-dimensional line will traverse the entire 2D plane, which is interesting mathematically. Also has some kind of interesting applications for projects, say, for this class. I had a student a few years ago, a group of students a few years ago, that used this as the basis of a sight-to-sound project. Based on, I believe, a 3 Blue, 1 Brown YouTube video that they had seen that talked about this as an application for the Hilbert curve. But what they did is they made a very low resolution picture. It was 8 by 8 pixels, and each of the pixels was either black or white. And so they could draw extremely simple pictures, smiley faces, for instance, or simple shapes, right? And then they used a Hilbert curve to describe an order in which to traverse those pixels to check if they're on or off. And so they'd start down here in the lower left, they'd step up, step over, step down, blah, 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 go through every pixel in their image. And then you could imagine taking that line and stretching it out, and associated with each point on the line where it's in the middle of a pixel, they would associate each of those points with an audible frequency, a different audible frequency, and then they generated 8 by 8 is 64 direct digital synthesis synthesizers so that they could synthesize all those frequencies simultaneously and play them. And what would come out is a sound that is a one-to-one map, a sound that directly maps to the image on the screen. And they did a pretty fascinating thing. They got this working maybe a week before the deadline and then tried earnestly to train their brains over the course of a week to learn how to see using this sound, with some success, fascinatingly. Not total success. With more time, they could get total success with this and higher resolution images and the whole thing. But they were able to do this sufficiently enough that we could draw a simple shape, and they could be looking the other direction, and we play the sound, and they'd go, kind of sounds like a square in the upper right corner. Yeah. So it's pretty fascinating. Let's see. So that would be an example of a sight-to-sound project. This whole idea of projects based on playing with your senses, augmenting your senses, is a whole really fun class of projects. So sensory augmentation is a great one. We all have 5 senses: sight, smell, sound, taste, touch, right? How about a 6th one? Wouldn't it be fun if you could, for instance, sense magnetic field? I would love to be able to do that, to just be able to always know where north is with the same ease that I can see things, for instance. And so could you build a device that, in a non-annoying fashion, the user of the device has this sensory augmentation, where they just always know where north is? There was a student project that tried this a number of years ago, before I was in this role. So I read about this project, but the project wasn't conducted while I was running the class, where, to my understanding, they made a belt, and on the belt they put a series of low-profile little vibration motors, little buzzers. And also on the belt, of course, was the microcontroller and a little magnetometer for north sensing. And they would just vibrate the buzzers in the direction of north all the time. So you'd wear this thing around, and as you're walking, you feel a little vibration around your waist in the direction of north. A fascinating thing happens with projects like this, where for a while you wear that thing and you notice the buzzing, and then after a while your brain just turns that off. It just stops noticing the buzzing, and instead you just know where north is all the time. So I could imagine versions of that project that perhaps augment you with a magnetic field sense. Using that strategy or a different strategy, you might be able to come up with other ways of giving magnetic field information to the user. But if you're interested in this idea of sensory augmentation, an amazing rabbit hole to go down is look around in the animal kingdom and try to do some research on some of the extra senses that some animals have that might be fun for us to also have. For instance, have you ever seen the eye of a cuttlefish? Cuttlefish pupils have this very strange shape, which, to my understanding, gives them they are able to easily sense the polarity of light. Turns out we can sense the polarity of light a little bit. They can sense it really well. This is of value to cuttlefish, which live in the sort of 3-dimensional underwater environment, because one's orientation in an underwater environment is less obvious than it is here on Earth, where we always have gravity pointing down, right? And so the sunlight coming through the water, that affects its polarization, and by being able to sense the polarization with their eyeballs, they get some information about how they must be oriented underwater, which is helpful to them. I could imagine building a system that gives us that sense to some regard. So like a hammerhead. And then essentially solving Laplace's equation, right? I mean, how cool would that be, right? So you could build a device that gives you this sense, where you are getting a sense of the, potential around you. And if you think a little bit and do a little bit of research, I'm sure that you could come up with other senses that would just be a blast to add to your repertoire of senses. I had a friend, by the way, this is just an aside, who got a little too into this idea of sensory augmentation and had a strong permanent magnet embedded surgically under the skin of his finger. And the consequence of that is he worked with high-power electrical systems. He could wave his hand near wires and feel whether or not there was current running through them. Kind of cool. He's since had it removed, as far as I understand. He couldn't get near any of the sensitive equipment at his workplace, right? Which was a pain. So this whole class of projects devoted to sensory augmentation are just really interesting. There's a related class of projects, sensory replacement, where you take something that we are really used to experiencing with one sense and figure out how to translate it to another sense so that you get a new experience of a very familiar thing. I gave you one example of that with that sight to sound project where you're taking visual information and figuring out some way to map it to auditory information so that you can see things that we're used to hearing. A fun version of this, I'll just mention, is I experimented with this just a little bit. I quite like these line drawings by Picasso that take some thing, and the idea here, to my understanding, is to what extent can you abstract it and that thing remains recognizable as the thing, right? To what extent can you abstract a bull that we look at that and we know that's still a bull, even though it's almost entirely abstracted away. And so there's this whole collection of interesting studies in this, where he takes things and tries to simplify them. But what you end up with is, in many of these, things which are either closed curves or very well approximated by closed curves. And any closed curve we can draw using Fourier analysis, right? So you make a bunch of sine waves, right, that describe the XY movement of your trace here. Make a different collection of sine waves that describe the up-down movement of that trace. And you move your little trace according to all those sine waves, and it will trace out a closed curve. You have to figure out what is the amplitude of each sine wave, right, in order to make the picture that you want, which is, as it turns out, can be done in a relatively straightforward application of Fourier analysis. But what then is fun is you can take these sine waves, here for instance is a rooster, draw a rooster. You can do a few fun things. One is you can draw different pictures with the same collection of sine waves by changing the amplitudes of each of those sine waves. So for instance, you have a whole bunch of sine waves of a bunch of different frequencies. Set to one set of amplitudes, it will draw a rooster or a dachshund or something like that. Set to a different set of frequencies, it will draw something else, but it's composed of the same sine waves, just of different frequencies. So if you have two images, and you figure out the set of amplitudes associated with this image and the set of amplitudes associated with this image, and then you smoothly change all the amplitudes from one into the other, the consequence is that you can smoothly morph one picture into another picture. Which makes for, I think, really nice little animations. And then, this is all in the context of a conversation about sensory replacement. There's a degree of freedom here. What matters when drawing these pictures is the relative frequencies of the sine waves. The degree of freedom is you get to pick the base frequency against which all the other ones are then relatively computed. If you choose a base frequency that is audible, then all those sine waves are audible frequencies, and you can generate a sound based on those sine waves in addition to a picture. This, by the way, it's going to be a funny anticlimax. I put this together with the idea that, like, oh my God, we're going to be able to hear Picasso. Like, it's going to be this big moment. Here's what that sounds like. I mean, okay. But then the fun thing you can do is, of course, you put a scope into XY mode so that one set of sine waves is controlling movement this way, the other this way, and you can draw the pictures onto the scope and hear them as you're drawing them. This I mentioned when we were talking about direct digital synthesis. I was talking about how we're using this for sound production, but is a generally useful algorithm, right? All of the sine waves associated with each of these pictures is generated by direct digital synthesis, a bunch of DDS waves. I've had some students in the past, let me see if I can find this, who really were delighted with this idea of using the oscilloscope as your display. Which, by the way, is an old idea. I mean, back in the day, that's, for example, had a group of students implement the first video game ever. First video game ever was a game called Tennis for Two. I can show you a demo of it here in a moment. But it was played on an oscilloscope, and there was a little tennis net, and you could see a little ball on the oscilloscope going back and forth, and the user would push a button, and that would hit the ball back. So you would play this game on the oscilloscope. These folks, let's see, does this work? These folks rebuilt this video game using the RP2040 and the two outputs of the DAC in order to, in XY mode, draw a display up there. Let's see, that's not a great one. In any case, you can go take a look at this if you want. The result was really, really nice. I've had other groups, let's see. Was this with PIC32 or with RP2040? Well, I'll talk about it. I had other groups that got interested in this idea of being able to draw things on the scope and listen to them simultaneously. So circles, you can imagine, are kind of easy. You generate a sine wave, you generate another sine wave 90 degrees out of the phase with the first, put it out of two channels, put the scope in XY mode, and you're going to get a circle out, right? One describing the X motion, the other. But replace the sine waves with triangle waves, and you get a nice diamond out. And so what these folks did is, in order to draw a desired picture, they figured out what is the periodic waveform, some weird shaped periodic waveform that we can generate in order to make the picture that we want to make on the oscilloscope. And then we make a sound associated with it. So scope as display is just, there's a whole great class of projects there. The old cool green screen with, you know, the little beam going across. They look great. Okay. Oh my God, we're almost out of time. Okay. So given that we're almost out of time, let me just go through a few other sort of ideas here. I hesitate to even mention this. How about Doom? Folks have done it. I've seen projects online where people got Doom to run on the RP2040. Do not undertake that project lightly. I mentioned early in this class that a whole fun class of projects are those that use some engineering project as the mechanism to learn a little bit more about something outside of engineering. So let's say, for instance, you're really interested in history. You might consider you could build an emulation of an Enigma machine. The Enigma machine being the enciphering machine used throughout World War II by a bunch of different nations, but by most famously and ubiquitously by Germany, cracked by Alan Turing, right, and his colleagues at Bletchley Park. They built the Bomba machine, which cracked the Enigma machine, thought to be uncrackable. Wouldn't it be interesting to build your own version of the Enigma machine and then take 5760 and build a Bomba machine on the FPGA and crack your own Enigma machine? These projects are such a blast because, you know, you can read about these historical engineering projects, and reading about it teaches you about it in a certain way, but building the thing yourself gives you such an intimate understanding of what these famous historical figures were thinking about. Right? If you build an Enigma machine, you get such an appreciation for the challenge that Alan Turing was facing and his colleagues at Bletchley Park. Build a Bomba machine in 5760, and you will have a more unique understanding with Alan Turing's mind than a lot of people, right? Because you will implement his design. That's a really rare opportunity to interact with a historical figure that way. Related, the Apollo guidance computer could you build yourself a nice little emulation of the Apollo guidance computer? It only had a few instructions. It had a very simple interface. I could imagine an RP2040 version of this that allowed for you to dork around with it in the way that perhaps the astronauts may have during the Apollo missions. There's a whole class of projects based on physics simulations, which are just a blast. Build n-body gravity simulators and observe what happens as things orbit one another. You could make, in lab 1, we spent a bunch of time looking at the audio spectrogram of a cardinal's birdsong. Maybe some of you looked at that and thought, ooh, I wonder if I could make a sound that drew a picture in the spectrogram of the sound. There's a whole delightful group of people that do this sort of as a hobby. So you, as we saw in lab 1, you make one frequency and you modulate it, and you end up with one line that you can move up and down through your spectrogram, right? But you can make a whole bunch of independent DDS synthesizers, make a whole bunch of different lines all moving up and down on the spectrogram. Could you write your name? And we could listen to what your name sounds like in cursive or something. That could be a fun class of projects. Slightly more like engineering flavored, we program our RP2040s generally by way of that USB connection, or perhaps you program it through the debugger. But that's the mechanism by which we get a program that we've written, some executable file, into flash memory on the RP2040, and then sort of automatically there's a bootloader in there that points the execution pointer to the right place, and that program runs. But you could write your own custom bootloader. This is a slightly more low-level project, but it's totally tractable and totally doable in the amount of time that you have. But if you write your own third-stage bootloader, for instance, you could allow for the user to program the device by some unconventional mechanism, like maybe through a speaker and a microphone, right? So you associate a certain sound with ones and zeros. Maybe you generate 16 different sounds for all the hex digits so that you can blast this thing with sound, and then suddenly Blinky starts running. It'd just be really interesting. Or color or something. You know, you can get some unconventional, interesting way of getting a program into the microcontroller. You could do sound localization projects. The speed of sound relative to the clock rate of the RP2040 is slow. So that means if you have a few microphones not that far away from one another, you can reasonably measure the difference in the time of arrival of a sound to those microphones and localize where the sound must have come from. It's a great class of projects. Other audio-related projects, you could do head transfer functions. So you might not have thought about your ability to do this, but we all have a pretty remarkable ability to, if we close our eyes and a sound occurs, we can point at the source of the sound. We're good at localizing the sound based on the way that we hear it. The reason for that is if a sound comes from some direction that's not right in front of us, there's a small difference in time of arrival from this ear to this ear. And furthermore, our head and our hair and the folds of our ears modify the wave, the sound wave, a little bit from one side to the other side, and your brain has been trained up to be able to recognize different changes and their mappings to different locations. Fascinating experiment. Well, part of your ability to do this comes from the folds in your ears, which act like really good interferometers for sound waves. Fun experiment to do is get some like silly putty or clay and just fill up your ear a little bit on both sides, and you will lose your ability to localize sound. Pretty fascinating. But yeah, Bruce? Don't put it in your ear canal. Don't put it in your ear. Just outside. That's all you need to do, and you'll lose your ability to localize. But there's so that's just a transfer function, right? You can implement that transfer function, and the consequence is you can put on earbuds and generate sounds with the RP2040 where you get to decide where the sound appears to emanate from. So you could, for instance, generate a little fly that flies around the person's head, and you put on the headphones, and it sounds exactly like something is moving around your head. If you Google around on YouTube for head transfer function demos and listen to them with headphones, there's some really great examples of this. Audio synthesis, musical-based synths are great classes of project. You could do additive synthesis to try to emulate the power spectrum of some instrument. You use FM synthesis, something that perhaps I'll talk more about in a coming lecture, to generate weird sounds. You can do physical synthesis, where you solve the physics of the instrument that you're trying to emulate and generate the sound based on the solutions to the differential equations that describe that system. This sounds hard, but turns out for some instruments is alarmingly easy. If you want to generate stringed instruments, there's an algorithm called the Karplus-Strong algorithm, which is a solution to the wave equation. It's very computationally lightweight, doesn't take much work at all. You can generate a whole bunch of different strings, and it will make beautiful simulations of things like guitar plucks or violins. Oscilloscope as display, I mentioned. You can make a speech vocoder, something that you talk into a microphone, and what comes out of the speaker is not your voice, but instead a series of sine waves of specific frequencies with amplitudes set by the frequency content of your voice. I'm not describing that exactly well, but you can make a system in which you talk into the microphone and a purely robotic voice comes out the other end. You're synthesizing a voice based on what you're saying. You can build robots. Here's a whole class of projects that hadn't occurred to me before, but that for personal reasons are top of mind. Baby toys. We have a bunch of baby toys kicking around our house right now, and so many of them look like awesome 4760 projects. If you choose to make a baby toy and you make it safe, I can offer a baby to test it. We're out of time. Yeah. Oh, video games, sure. Yeah. Let me just say before we go, to reiterate Bruce's point, a lot of the stuff I talk about you could use as a premise in a game that you play. Video games make for great final projects because you test them by playing them, and there's a strong motivation to optimize because you're the player and you want for the playing experience to be better. So people that make video games often end up making really nice projects because they just get frustrated with the playing experience and they get obsessed with making it better. But any of that stuff, you could imagine making a spectrogram-based video game or something. Oh my God, yeah. Let me just, before we go, let me show you. One of the most exquisite that I've seen. These folks made a beautiful, beautiful emulation of the original Legend of Zelda game. All of this artwork was lovingly bitmapped by them in Google Sheets. They had background music, they had sound effects, they had custom little sprites that would change their orientation as they walked. The legs would move as they walked. This was so good that at the end of the class last year, some folks from ASML, the big company making lithography machines, came to visit the lab, and this was up, and these folks got job offers on the spot. They sat down and played Legend of Zelda and said, do you guys want to come work for ASML? I mean, it was just exquisite. I had another group a handful of years ago make a similarly beautiful emulation of PacMan. Sounds easy, but when you actually dig into how PacMan works, there's every ghost has a different set of rules associated with it. Anybody know the ghosts' names, by the way? Inky, Blinky, Pinky, and Clyde. Inky, Blinky, Pinky, and Clyde all move according to different rules, and those rules are functions of the relative position of PacMan relative to the ghost. They got all of this implemented so that it was a perfect reconstruction of the first level of PacMan, a truly epic amount of work. So video games are great. Yes, that's a whole... So, I would recommend, like I said last time, make a list of stuff you're interested in. That's very helpful for coming up with project ideas. Look through previous student projects. These are all the RP2040 projects, and then if you click this link, you'll find all the student projects going back years and years. PIC32s and other microcontrollers going back to, whatever year, 99 here. It's kind of fun to just look at some of these old things as well. So in any case, I'll be delighted to talk to you about your project ideas in lab or elsewhere. Please think about it. Like I talked about last time, It's a long project. So you want to do something that you're enthusiastic about because it makes it a blast to work on it. So give some thought to what you would like to spend your time doing. And if it's helpful, we can have another conversation like this, if folks would like to. Maybe an approach we could take is after we just sort of brain dumped a bunch of stuff, maybe people could go think about some things and we could come back and have a conversation about more specific ideas, if that would be helpful. In any case, I better get out of here. I see folks at the door. But give it some thought.